เคผ่านไป1 ชั่วโมงก็ต้องมาทำควิซใหม่อีกรอบหนึ่งปัจจุบันไม่ขึ้นนี่เป็นอะไรที่เป็นมาคอฟไทม์ทีมากกว่าเท่ากับ0ปัจจุบันแล้วอนาคตก็จะไม่ขึ้นกับอดีตใช่ไหมอันนี้ตั้งแต่แรกเริ่มเดิมที initial state จนถึงอดีตไม่ขึ้นกับอนาคตอะไรวะเนี่ยปัจจุบันอนาคตไม่ซิมันขึ้นกันซิต้องอันนี้ต้องปัจจุบันปุ๊บอันนี้ In the following dynamic Bayesian network, which the following independent assumptions are true? อันนี้อันหนึ่งถูกไหมมันคือข้อเมื่อกี้ observe ของอดีตไม่ขึ้นกับ observe ของปัจจุบันถ้าเกิดในอดีตปุ๊บปัจจุบันอนาคตไม่ใช่สิโอเคอันเดียว application predict ของ dbn predict probability today snow today yesterday 3 วันก่อนหน้าไม่ใช่เนาะ location many other location ไม่ใช่เนาะ modeling time series data event but only the event of the time one time point directly before it okay predicting the probability today วันนี้ฝนหิมะตก when this value depend only on whether yesterday was snowy okay A B random variable inside a common plate โอเคเริ่มพอเข้าใจ plate มากขึ้นละ index by I นี่เป็น random variable เนาะ A กับ B อยู่ใน plate เดียวกันก็เป็น stack ของ plate which of the following statement must be true ก็ต้องบอกว่า for each I AI BI have different ไม่ใช่น่าจะเป็นthere is an instead of A and instead different CPD ถูกแล้ว same ไม่ใช่แน่ๆใช่ไหม for each I are not independent there is an instance of A and of B อันนี้สิมี instance of A แล้ว B for every I CPD ไม่เกี่ยวจริงๆแล้วอาจจะเท่ากันก็ได้แล้วแต่ใช่ไหมไม่เท่ากันก็ได้เนาะโอเคต่อ page interpretation อันนี้ก็คือถามว่า which of the given instance of X does it represent the grounded model whether specific teacher T นะ taught a specific course C at school S ต้องมี T C S แน่ๆถูกไหมถ้าเราพูดถึง X อันนี้ same project เดียวอันนี้เราก็รู้แล้วว่ามันต้องเป็นถ้าเป็น X ก็ต้องเป็นไม่ใช่ X สิ S T C difficulty เนาะ difficulty คือนี้ก็ต้องมี C กับ S แน่ๆ C S อันนี้ template model อันนี้ก็มี K market L product M consumer N location ถามว่า P integrated B and how many instances โอเคก็ต้องมี P ก็ต้องมี product ก็คือ L consumer M L คูณ M L multiply by M and multiply by the plate นี้ M K เป็น K market K L M N location ไม่เกี่ยว template model also the plot model of the previous version what might P represent ก็ต้องเป็น specific product นะ was consumed by consumer C in market M ตัวนี้แค่ตัดแค่นี้นะต่อไปแค่นี้นะนี่อะไรยาวๆเฟ้ยอะไรไม่รู้ time series graph which of the time series graph satisfy what โอ้มันไม่มีรูปขึ้นอ่ะลุกขึ้นละมาคอฟก็ต้องอันนี้ผลต่อหน้าอันนึงถูกไหมคือเป็นอันนี้นี่ถ้าเป็นอันนี้ยิงไปยิงกลับอะไรไม่รู้ว่าบีบอันนี้ถามว่าอันไหนที่เป็นได้ตามนี้ก็คือ xt dividend กับ c at time t given y at time t ก็ลองคิดภาพอันนี้มันตอบมาอีกอันลง observe ไปลง observe มันก็มีขีดเหมือนกันนะสำหรับอันนี้ที่time t บวก1ใช่ถ้า y มันถูก observe ที่ time t ปุ๊บมันก็จะส่งผลต่อ x ส่งผลต่อ x ที่ time t บวก1ส่งผลต่อ y แล้วส่งผลต่อ c เพราะงั้น x ส่งผลต่อ c อันนี้ก็ถ้ามีขีดมาเส้นเดียวนะแล้วก็ลงแล้วก็มี observe ถ้า y ถูก observe ปุ๊บก็ given y นะ y observe ปุ๊บมันก็ไป x ใช่ไหม x ไป x เหมือนเดิมแล้วก็ลง y ลง c เพราะฉะนั้น2เนี่ยไม่ independent กันถูกไหมใช่ไหมมันต้องเป็นอย่างนั้นสิ observe ด้วยเนาะถ้า observe แล้วเนี่ยoverall t ถ้าอันนี้ y observe ปุ๊บอันนี้ observe อยู่แล้วถูกไหมเพราะงั้นอันนี้ก็ต้องส่งผลต่ออันนี้ตัวนี้ถูกป่ะเพราะมัน activate อยู่แล้วอ๋อเพราะงั้นอันนี้มันก็จะส่งผลต่ออันนี้ y ที่มัน observe มันก็ส่งผลต่อ x ส่งผลต่ออันนี้ x อันนี้มันเป็น t บวก1นี่มันไม่ใช่ time t เนาะแสดงว่าไม่เกี่ยวเพราะงั้นเราก็ต้องพูดถึง time t ของเราเนี่ยเหมือน y ถ้า observe นี่ observe ใช่ไหมอันนี้ก็จะไปเกิด reactivate ก็คือ x ส่ง y ส่งผลต่อ observe ส่งผลต่อ c แบบนะงงไหม แต่ y ที่มันมาตัดนะตัดตรงกลางอันนี้ก็เลยมันไม่ลงมาไม่ถึงนะขั้นไว้ y นี้ก็มาตัดตรงกลางเหมือนกันนะแต่ y นี้ x y c ด้วย observe น่าจะอันนี้นะโอ้ผิดอันหนึ่งผิดข้อไหนก็ยังผิดข้อเดิมต่อถูกแค่ข้อเดียวคือ b The independent attention hold in this network because knowing y block ก็คือบล็อกตรงกลาง what only trail from x to c มี active path from x to c ได้ through the previous time step ก็คือสมมุติอันนี้ต่อไปก็จะมี x t by x t ลบ1 y t ลบ1 c t ลบ1 4มี active path จาก x t ไป c t ได้มากันแล้วแต่กันไม่สุดมันมาทางนี้ได้นี่มันกันสุดเลยนะกันไปทั่วเลยงั้น x ไปทางนี้ส่วนนี้ y ก็กันแต่มีอันนี้v activate อยู่ต่อนี้ independence
So we previously talked about the importance of allowing CPD representations that encode additional structure in the local dependency model of a variable on its parents. And we talked about the case of tree CPDs, which allow us to depend on different variables in different contexts. But none of that helps us deal with the situation that we used as a motivation for this, which is where we have a variable such as, for example, cough that depends on multiple different factors: pneumonia, flu, tuberculosis, bronchitis, and so on and so forth. This doesn't lend itself, say, to a tree CPD, because it's not the case that you depend on one only in certain contexts and not in others. Really, you depend on all of them, and all of them sort of contribute something to the probability of exhibiting a cough. So one way for capturing that kind of interaction is a model called the noisy OR CPD. And the noisy OR is best understood by simply considering a slightly larger graphical model where we break down the dependency of y on its parents x1 up to xk by introducing a bunch of intervening variables. So let's imagine that this is, again, like cough variable. And this is different diseases, for example. And what we're doing here is we're introducing an intermediate variable that captures the event that this disease, X1, if present, causes a cough by itself. So this is X1 by itself causes a cough, or causes Y. You can think of it, each of these as a noisy transmitter. If you have the disease, say if X1 is true, then Z1 sort of says, fine, X1 succeeded in its intent to make Y true. X2 has its own little filter called Z2, and Z2 makes that same decision relative to X2. And so ultimately, Y is true. So Y is true if someone succeeded in making it true. Which means that Y is a deterministic OR of its parents, Z1 up to ZK, Z0 up to ZK. So now let's make this a little bit more precise. So the probability of Zi being true given Xi, there's two cases. If Xi equals 0, well, Xi isn't even trying to make Zi true. So in this case, the probability of Zi equals 1 is 0. Okay? If Xi is not true, Zi doesn't get turned on ever. If Xi is true, then there's some probability for Zi to get turned on, and that probability is something called lambda I. And lambda I is in the interval 0, 1, and you can think of it as defining some kind of penetrance of how good is Xi at turning Y on. So if we actually write this down as a probability, and we just consider the CPD of Y equals 0, so Y doesn't get turned on, given some set of cases X1 up to Xk. So now we're asking, what is the probability that all of these guys fail to turn on the variable Y? So what I forgot to say is that Z0 is what's called a leak probability, and that's the probability that Y gets turned on just by itself. And that happens with probability lambda 0. So when does Y fail to Y gets turned on just by itself? And that happens with probability lambda 0. So when does Y fail to get, and that happens with probability lambda 0. So when does Y fail to get turned on? First of all, when it doesn't get turned on by the leak, so that's 1 minus lambda 0, times the probability that none of the causes that are on, so none of causes that are on, which are the Xi's that are equal to 1, turn of causes that are on, which are the Xi's that are equal to 1, turn Y on. And so that's a product of 1 minus lambda I for all of the Xi's that are on. That gives us the probability of y equals 0, and obviously the probability of y equals 1 is just the complement of that, 1 minus. Sorry, this should be 0. Good. So that's the noisy or CPD. And you can generalize this to a much broader notion of independence of causal influence. This is called independence of causal influence because it assumes that you have a bunch of causes for a variable and each of them acts independently to affect the truth of that variable. And so there's no interactions between the different causes. They each have their own separate mechanism, and ultimately it's all aggregated together in a single variable z, from which the truth of y is then determined from this aggregate effect of all of the effects zi's of the different causes. So one example of this is we've already seen the noisy OR, but you can easily generalize this to a broad range of other cases. There's noisy ANDs, where the aggregation function is an AND. There's noisy maxes, which apply in the non-binary case when causes might not just be turned on or off, but rather they have different sort of extents of being turned on, and then Z is actually sort of the maximal extent of the independent effect of each cause, and so on. So there's a large range of different models, all of which fit into this family. Noisy OR is probably the one that's most commonly used, but the other ones have also been used in other settings as well. One model that might not immediately be seen to fit into this framework, but actually does, is a model that corresponds to the sigmoid CPD. So what's a sigmoid CPD? A sigmoid CPD says that each xi induces a continuous variable which represents wi xi. So imagine if each xi is discrete, then zi is just a continuous value wi, which parameterizes this edge. And it tells us sort of how much force xi is going to exert on making y true. So if wi is 0, it tells us that xi exerts no influence whatsoever. If wi is positive, xi is going to make y more likely to be true, and if wi is negative, it's going to make y less likely to be true. All of these influences are aggregated together in this expression for the variable z, which effectively adds up all of these different influences plus an additional bias term, w0. And now we need to turn this ultimately into the probability of the variable y, which is the variable that we care about. And in order to do that, what we're going to do is we're going to pass this continuous quantity z, which is a real number between negative infinity and infinity, through a sigmoid function. The sigmoid function is defined as follows, and it's a function that some of you have seen before in the context of machine learning, for example. So sigmoid takes the continuous value z, exponentiates it, and then divides by 1 plus that exponent of z. And since e to the power of z is a positive number, this gives us a number that is always in the interval 0, 1. And if we look at what this function looks like, it looks like this. So this is the sigmoid function. The x-axis here is the value z, and the y-axis is the sigmoid function. And you can see that as z gets very negative, the probability goes to 0. As z gets very high, the probability gets close to 1. And there's this interval in the middle where intermediate values are taken. So this is kind of like a squelching function that, that sort of squashes the function on both ends. Let's look at the behavior of the sigmoid CPD as a function of different parameters. So here is a case where all of the xi's have the same parameter w. And so what we see here is the value of this parameter w, and over here is the number of xi's that are true. So let's look at first this axis over here. The more parents that are true, the more parents that are on, the higher the probability of y to be true. Okay? And this holds for any value of w because these are all positive influences. Okay? So the more parents are true, the more things are pushing y to take the value true. This axis over here is the axis of the weight, and we can see that for low weights, you need an awful lot of x's to get y to be true, but as w increases, y becomes true with a lot fewer positive influences. This graph on the right now is what we get when we basically just increase the amplitude of the whole system. We multiply both w and w0 by a factor of 10. And what happens is that means that the exponent gets pushed up to extreme values much quicker. Z gets effectively multiplied by a factor of 10, and that means that the transition becomes considerably sharper. That gives us a little bit of an intuition on how the sigmoid function, on how the sigmoid CPD behaves. So what are some examples of this kind of of an application of this? So I showed this network in an earlier part of this course. It's the CPCS network, and it's used for, it was developed for here at Stanford Medical School for diagnosis of internal diseases. And so up here we have things that represent predisposing factors. And there's actually a fairly eclectic range here. So for example, one predisposing factor is intimate contact with small rodents, because that's the contributing factor to hantavirus. And so there's a whole range of predisposing factors. Down here in the middle, we have diseases. And down at the bottom, we have symptoms and test results. Now, as I previously mentioned, there is approximately 500 variables in this network, and they take on average about 4 values. So the total number of entries in a joint distribution over this space would be approximately 4 to the 500 different parameters, which is clearly an intractable number. If we were to take this network and if we take this distribution represented using the network shown in this diagram, we get considerable sparsification, and the factorized form has approximately 134 million parameters, which is still much too many to have a human estimate. By using, as in this case, they used a noisy max CPD, they brought the number of parameters to about 8,000 total parameters for this network, which is a much more tractable number to deal with. CPDs that exploit additional forms of local structure, some kind of parametric form, are extremely valuable in the context of in the general context of graphical models, because they allow us to provide a much sparser representation. But they're absolutely essential when we have a network that involves continuous variables, because their tables are simply not an option. So let's look at some examples of networks that involve continuous variables and see what kind of representations we might want to incorporate here. So now let's imagine that we have a continuous temperature variable, say the temperature in a room, and we have a sensor, a thermometer that measures the temperature. Now, thermometers aren't perfect, and so what we would expect is that the sensor is around the right temperature, but not quite. And so one way to capture that is by saying that the sensor S is a normal distribution. So here's a normal distribution around the true temperature T with some standard deviation, sigma S. So this defines for every value of T a distribution over S in a very compact parametric form that has just really the parameter sigma S, and we just say that S is Gaussian around the variable, around the value of the variable T. Now let's make the situation a little bit more interesting. This is the temperature now, and this is the temperature soon. So we have T and T prime. Now, T prime now the temperature soon depends on the current temperature, as well as on the outside temperature, because of some equalization of temperatures from the inside to the outside. So what model might we have for T prime as a function of its two parents, temperature, the current temperature and the outside temperature? Well, so one model might be just some kind of diffusion model that says that T is equal to some weighted combination T prime is a Gaussian around a mean that's defined as a combination of the current temperature and the outside temperature. So you kind of combine the two, and because there's stochasticity and noise in the process, we're going to say that T prime isn't exactly equal to this, but rather is a Gaussian around this mean with some standard deviation sigma t, to be distinguished from the standard deviation sigma s, which was the sensor variance. Let's make life even more interesting. Let's imagine that there's a door in the room. The door can be open or closed. So it's a discrete variable, takes two values. And clearly, the extent of the diffusion is going to depend on whether the door is open. And we would expect different parameters to the system in the case of the two values of a discrete variable. And so if we write the model now, we're going to have that the temperature at time, the temperature soon, T prime, is going to be a Gaussian that whose parameters, alpha and sigma, depend on the value of the door variable. So if d equals 0, we're going to have parameters alpha 0 and sigma 0 t. And if d equals 1, we have a different set of parameters that reflect a different diffusion process. So just to give all these things names, this model that we had over here was called a linear Gaussian. We'll define that more formally in the next slide. And this model is called a conditional linear Gaussian because it's a linear Gaussian whose parameters are conditioned on the discrete variable door. So to generalize these models to a broader setting where we have a general variable y, and y has parents x1 up to xk, the linear Gaussian model has the following form. It says that y is a Gaussian, so that's what the n stands for, whose mean is a linear function, and that's why it's called a linear Gaussian, is a linear function of the parents xi, and importantly, whose variance doesn't depend at all on the parents. So the variance is fixed. That's the definition of a linear Gaussian CPD, and obviously it's restricted. It doesn't capture every situation, but it's a useful model and a useful first approximation in many cases.
LV เป็น location velocity ของรถ Assume that CPD on the light is a linear Gaussian. Which of the following statements could possibly be consistent with that CPD? Velocity location ไป CPD on the light distance move อันนี้จะไม่มากกว่า2คูณ v delta t watt L t บวก1 end up from its expected position. Cars that move faster skid more and have great variance in position. อะไรวะ Due to friction, the single most likely value for L. L บวกไม่ใช่นี่แล้วกัน นี่ด้วยเหรอ the single most likely value most likely นะ คือมีนนะน่าเป็นมีน variance condition
Conditional linear Gaussian introduces into the mix the possibility of one or more discrete parents. In this case, we just drew one for simplicity, but you could have more than one. And this is just a linear Gaussian whose parameters can depend on the value of A. So, writing it down, it looks exactly like this. We now have, for every one of the parameters, we have the ability for the parameters to depend on A. And in this case, the variance can depend on the discrete parent, but not on the continuous ones. And this is the conditional linear Gaussian model. And again, similarly, it's a restricted model, and one can certainly generalize beyond that, as we'll show in a moment, but it's a very useful model that's used in a large number of applications. One example application that we've seen that involves continuous variables is the task of robot localization. I'm not going to show this video again now. We're going to see it again when we talk about temporal models. But just as a reminder, what we have here is a robot whose location is a continuous quantity. So are the sensor observations that give a noisy version of how far away the robot is from an obstacle looking in each one of the different directions. Okay? And so we have both a continuous state variable as well as continuous observations that the robot needs to deal with. So what kind of observation model makes sense in this setting? So here, let's imagine that this line over here represents the true distance from the robot's current location, from a given location to an obstacle. So if the robot is looking if we're conditioning on the robot's current location, and we're asking, if I look in this direction, how far is it before I hit an obstacle? In this case, that distance is 220 centimeters. And what this tells us is that a sonar is a Gaussian. You can see this is the sonar, the red is the sonar, is a Gaussian around that true distance. Now, the distance, continuous observations that the robot needs to deal with. So what kind of observation model makes sense in this setting? So here, let's imagine that this line over here represents the true distance from the robot's current location, from a given location to an obstacle. So if the robot is if we're conditioning on the robot's current location, and we're asking, if I look in this direction, how far is it before I hit an obstacle? In this case, that distance is 220 centimeters. And what this tells us is that a sonar is a Gaussian. You can see this is the sonar, the red is the sonar, is a Gaussian around that true distance. Now, the laser, which is a different sensing modality for the same robot, is also a Gaussian around that true distance. But because the laser is a more accurate sensor, the standard deviation is lower for the laser than for the sonar. And that reflects the accuracy of these two different sensor modalities. Now, this is an idealized version, but surprisingly, it corresponds in useful ways to the real model. So let's actually look at some of the, let's look first at the model that was used in the system, and then which is the red line, and then we can look at the blue line. The red line actually involves three different components. So this is the actual sensor model used by the robot. And we can see that it has three components. It has this peak, which is this Gaussian around the true distance. The next most obvious phenomenon is this ridiculous peak over here. This corresponds to a max range reading. This is what you get if there isn't an obstacle in that direction within a reasonable distance for the laser or the sonar to return any signal. And so that's why there is a very large peak beyond a certain distance. That's the entire rest of the probability mass. The final, more subtle aspect of this probability distribution is that you see that this is higher than that. So there's more probability mass for the density before the obstacle than after the obstacle. And why is that? Because once you get to the obstacle, the beam returns. But before you get to the obstacle, there might be some other transient things, like a person walking in front of the obstacle, and that's going to return the beam in a way that doesn't represent the actual structure of the map. And so that's why we have a certain probability of having the beam return sooner than the obstacle, and that probability doesn't exist on the downside once the obstacle has been reached. So the actual probability distribution is an aggregation of these three signals: the sensor model around the obstacle in a given direction, this uniform distribution before the obstacle, which for just a spurious return, and the max range reading at the end. The red line is the model that was used, and the blue line is the actual measured distances in different settings to sort of show whether this really does, the model that was used really represents reality. And the answer is that it does to a surprising extent. So this is an example of how continuous distributions are going to be used in a real-world application. The next example of that is actually in the robot motion model. So here's a robot, and the robot is heading in a given direction, alpha. Okay, heading in this direction. That's where it thinks it's going. And the question is, if it moves a certain distance, it thinks it's moving a certain distance in a given direction, what is the actual distribution over its next location? And the answer is, it's a little bit tricky because robots actually have a heading, and there's a certain uncertainty, alpha, over, which is a difference between where they think they're going and where they're actually going. And then there's also noise on the distance delta that they think they moved. And so when you put all these together, the actual cloud on the distribution, on where the robot's going to be following the move is this weird banana-shaped distribution, which is centered around this area where the robot thinks it is, but has a sort of banana shape that's where the banana shape is induced by the uncertainty about the angular trajectory. And if you actually run this for a while, you can see that the banana shape gets more and more and more diffuse. So here's the first banana shape, and now the robot turns, and there's more uncertainty over the heading. And so you get a larger and larger banana-shaped distribution on the robot's position, assuming that there's no evidence to correct the position based on, say, sonar or laser readings.
Consider the CPT below. What is the probability that E เท่ากับ E 0 A B C D given E okay. Using the graph given an observation A เท่ากับ A 1 B เท่ากับ B 0 C เท่ากับ C 0 D เท่ากับ D 1ต้องอันนี้เลย 0.9 ป่ะไม่รู้เลยตอบไปก่อน Denote B is a deterministic function of its parent A. Which of the following is an independent statement that holds in the network? When presentation let B no longer be a derivative function. How is parent A? Here the following is อ๋อที่เป็น deterministic function ศูนย์ e ศูนย์ a ศูนย์ e ศูนย์ t ศูนย์ a หนึ่ง no ศูนย์เลยเหรอขึ้นกับ a ถ้า a ไปฝั่งนู้นก็จบอ๋อเขาถาม e ศูนย์0.1สิเนี่ยเสียงอันนี้เข้าใจอันนี้เข้าใจอันนี้ไม่เข้าอันนี้ตอบผิดด้าน แค่นี้ก่อนเดี๋ยวที่เหลือค่อยมาตามเก็บพรุ่งนี้ทำการบ้านจะโปรแกรมมิ่ง Channel ไม่ควิสมีควิสด้วยแล้วก็มีโปรแกรมมิ่งด้วย